All right, why don't we go ahead and get started? So welcome back everybody to EE290C. Hopefully you guys had a good time at ISC. Just for sake of polling, I guess, how many of you guys actually checked out some paper related to what we've been talking about while you were at ISC? Wow, small group. Come on, you guys didn't. There was a ton of papers related to links. Nobody went. Okay, well, so just to sort of, let's say, slowly get us ramped back up to speed. So I did sort of take a look at the homework number 2s. I think largely speaking, people were sort of getting most of the stuff that I thought was important. There was a couple of relatively minor things that I just wanted to quickly go over because I saw them in a couple of places just to make sure that we're all on the same page on. The first was largely just a definitional thing. So when I say voltage margin, and I think most people that you talk to in the links community when they say voltage margin, what they mean is basically what I've drawn in the diagram here. So in other words, when they say voltage margin, if I had this eye diagram that looked like this, and your slicing level was kind of in the center of that eye, meaning at the 0 threshold, then when people say voltage margin, what they usually mean is the distance from that slicing threshold to the data level. Okay? So ideally that would be like half of the height of the eye, right? So that's called the margin because basically, if you had noise that was any larger than that amount, then you'd basically get an error at least on one half of the time, right? So I just wanted to clarify this here because there's a few people that quoted margin as not being the distance from the slicing level to the height of the eye, but rather the sort of peak to peak height of the eye. That's okay, like you can do that. It's just that if you do that, then all the numbers you use to sort of calculate noise sigmas, or rather to say sort of how much bit error rate you're going to get, would have to be doubled. So in other words, if you use the black number here, if you use that black line for voltage margin, then when I say 9 sigma is your voltage margin, that would give you 10 to the minus 15. If you use the blue version, then you'd need 18 sigma to get that same 10 to the minus 15 bit error rate. Does that make sense to people, or? Okay, good. So that's, again, largely just a definitional thing. The other one that I saw, which a couple of people sort of, didn't maybe quite get, or maybe they were just being a little bit too fast and loose, is, we talked a lot about sort of DFE versus linear equalizers and what it does from a noise enhancement standpoint and things like that. So in particular, there was that one problem where I basically told you that, your channel just looked like a very simple low-pass filter, right? And so basically almost all of you guys, or I think pretty much everybody, then realized that in the time domain, the pulse response of that looked something, of course, like this, right? So basically you had a sort of, exponential-ish looking initial rise, and then afterwards this long exponential tail that was basically coming back down, right? So most everyone, I think, or basically everybody figured out that one thing that's kind of interesting about this particular type of channel was that because there's a very well-defined relationship between each and every single value of the residual ISI, all it actually took for you to basically cancel all of the later taps was if just at one point you arranged it so that you had either a DFE or in this particular case the FIR that exactly put in enough energy to cancel that one thing, then all of the following taps would also be canceled because they were all just scaled copies of that same value. Right? So this worked particularly nicely on the transmitter. And then I also asked the question of, well, what happens if you actually use the DFE, right? So instead of doing some FIR filter at the transmitter, you also actually used, let's say, a DFE for one tap to just kill the immediate post-cursor, right? So what you would basically do then is, and we'll draw this actually again a little bit later on, so let's say that your initial thing, once you pre-emphasized it, when you pre-emphasized it, what you would have tried to do is make it so that each one of your non-cursor values was 0, right? But in order to do that, there was a certain amount of pre-emphasis you had to do, which caused you to rescale the whole value that you could actually transmit, right? Well, so when I say that you can actually leave one DFE tap behind, then that sort of means that you could actually now re-engineer your equalizer so that it looks like this, right? In other words, so that you don't have to scale quite as aggressively as you used to, okay? So again, actually, most people got this right, and they even figured out sort of what the relationship between the heights of those two things would end up being. The only thing that I saw a couple of people sort of not exactly get right was they said that, well, if I had an infinite number of DFE taps, then they actually had the margin go all the way up to the original transmit swing. So that, unfortunately, that actually would have been really, really nice if that happened. But why is that particular statement not quite correct? So the question is, again, I have an infinite number of DFE taps, and I just want to know what's the sort of, given a certain swing in the transmitter, what would be the margin that you could actually get out on the receive side, given this particular type of channel here. Yeah.
Don't you still have the loss due to the channel?
Yeah, exactly. So the trick here was that even if I kill all of these later taps, right? So I just completely eliminate them with the DFE. So my transmitter is really just a very dumb thing. All it's doing is just sending, ones and zeros, depending upon whatever the data level is. Then the thing to remember is that unfortunately, you still have some loss due to the low pass behavior of this channel, right? So in other words, if I looked at the time domain response, then all that would happen is that even with that DFE, basically I'd still have this thing that kind of looks like 1 minus e to the minus t bit over tau, right? That would be kind of like the height of my signal that I'd actually get, right? So that loss, unfortunately, you can't get rid of with the DFE, right? All the DFE does is just kill all of the taps afterwards so that they don't interact with each other. But you still, unfortunately, end up with this loss here, okay? So it's kind of just another way of saying that the DFE is just kind of a clever way of giving you a channel that basically looks flat, but it can't really get rid of the loss. It's better than a linear equalizer, but it still can't get rid of the sort of fundamental loss that you take on that one initial bit. Does that make sense to everybody? Or I guess in particular, you don't have to raise your hand or whatever, but for those of you guys who maybe didn't quite get it right, does that make more sense now? Or no one's fessing up, so okay, so any other questions on the homework or material so far before we dive back in? Or everyone's ready to go, huh? Okay, so what we were basically talking about, last couple of lectures, and I'll just bring us back there so that we can sort of, go over the pictures that we had, was we started really talking in detail about essentially how do we build these different types of equalizers that we've discussed. So we talked about continuous time linear equalizers. We then talked about FIR filters, and in particular we focused on the transmitter and some of the trade-offs there in terms of just how you'd go about building it and what some of these sort of implications would be on parasitic capacitance and power consumption. And then we finally got to the receive FIR filter. So this is still linear, not DFE, just a linear FIR filter. And we basically said that on the receive side, doing these FIR filters, at least at the moment, is not particularly popular. Okay, and we said that the main reason for that was that, generally speaking, when you build things on the receive side in terms of these FIR filters, that implies that you have to have essentially these analog delays, right? And those analog delays basically end up being some sort of sample and hold circuit, which then end up causing either distortion or power because you have to make sure that your noise is sufficiently small, and so on and so forth. So what we then started talking about was other ways you could build FIR filters in the analog receive domain. You could do it on the transmitter too, of course, but it doesn't really make too much sense. Where basically you just try to avoid these long sort of analog delay chains. Because remember, what's really nasty about analog delays is that every time you put a delay in there, you pick up more noise, right? So if you have a long chain of those things, you're going to pick up a lot of noise by the time you get to the end of the chain, okay? So what we started talking about was, as I said, these other alternatives for how you could build these receive analog FIR filters. And the one we started talking about was the so-called coefficient shuffling architecture, okay? So just to sort of briefly go over it, the basic idea here was that imagine that you basically have these sort of fixed multipliers with fixed coefficients, where these multipliers, again, in the analog domain would just be something like a GM cell, right? So imagine that what I basically do is if I have this sort of sample and hold array, well, what I could do would be, let's say that I wanted to build this particular filter where, as an example, this C0 is the main tap, C1 is, let's say, the first post cursor, and C2 is the second post cursor, right? So the basic idea would be that I could essentially sample these inputs in these three samplers here. Then in the first, for example, phase, feed them to these three multipliers, okay? So on that first sort of clock phase, I've gotten that filter that I wanted, right? Then what I do is in the next time phase, and the time phases here are obviously controlled by the clocks, and I'll draw a picture of that in 1 second just to make sure it's clear. What I will basically do is I'll just I can still take that same sample that I had from one time phase ago, but now since I've advanced by one time phase, its sort of meaning has shifted, right? So if before it was, let's say, the cursor, then now it would actually be the first post cursor, right? Because I'm one time sample later. Okay, so from that standpoint, I could just take that same sort of sample value, and instead of, for example, let's say on this guy it used to be x0, now instead of feeding it to c0, I instead feed it to c1, right? Because now it's supposed to be the first post cursor. Okay, and so you can imagine I can keep doing this rotation, and as long as I do the rotation correctly, and in this particular case I have to match the sort of number of samplers to the number of coefficients, then I can basically build it so that I never have cascades of these sample and holds, right? Because notice I've always just sample and held once. I'm just feeding that sample and held value to a bunch of different multipliers. Okay? Does this kind of make sense to people, or? Okay, so by the way, just maybe to make sure it's clear, and we'll draw a more detailed example of this in 1 second. Let's say we said that this is good because it gets rid of long chains of sample and holds. But what are you paying for it? What's the sort of trade-off that you have to make to actually get this to work?
More loading on VN.
Okay, that's right. You basically have more. Well, sort of. That's right. You sort of have more loading on VN, and how does that sort of scale with the number of taps?
Linearly.
Right. So the more taps you have, basically the more sample and holds you put directly on that VN node, right? Anything else that's more complicated now? Chris?
Oh, whenever you switch multipliers, there's like a charge sharing for the capacitor.
Okay, that's right. There is actually some glitches and things like that you have to worry about. That's actually a very good point. We'll see that in more detail in a second. Shiva?
You have so many switches and clock routing and...
There we go. Okay, so what really gets complicated is imagine you wanted to do this for 20 taps, or 40 taps, or 100 taps, right? Now I need 100 or 40 or 20 or whatever it is, different clock phases, right? And as you just said, this thing is going to become a big beast in terms of routing it everywhere and figuring out, which wire goes where. And actually, in fact, if you see this picture, it'll make even maybe more sense because this is just an example of how you might implement this. So by the way, you can do that shuffling either on the analog inputs or on the digital coefficients. Here I've just drawn it as being done on the analog inputs, and I've done it with this example of 3 things here. But actually that routing that we were just talking about, notice I had to take these 3 sampled inputs here, and then I had to route them to any one of these 3 multiplier cells, right? So I'm going to have this routing channel thing here that's going to be, actually internally is going to have a big fan out because each one of these has to connect to each one of these 3 at any one point in time, or potentially at any one point in time. But really in terms of space, you have to cover this big, long wire, right? So indeed, that's kind of why even if you do something like this, still, these particular filters, at least for long responses, tend to be not that popular. Because just basically the amount of hardware you need to kind of make it work nicely tends to explode. And just to be clear here, I've sort of drawn what the clocks tend to look like. It doesn't necessarily have to be this way, but usually you do indeed build them as these non-overlapping clocks. So in other words, each one of these clocks would be sort of 1 bit time wide in our particular context. Okay? By the way, that also has a sort of implication on how you'd actually sort of build the circuitry that generates these things. Because that implies that you need some counter running at the full bit rate, and then a whole bunch of comparators to figure out when is it that this particular clock phase is actually supposed to be high. Okay, so again, it's possible, but tends to have a lot of overhead and just take a lot of hardware resources to actually build something like this, especially if you want a fairly big filter at the end of the day. Okay. Does this make sense to everybody? Or? Okay, so there is one other thing that I wanted to just sort of briefly mention still in the context of receive FIR filters, which is just that, again, there's actually some other tricks you can play that turn out to be actually sort of fairly similar to the tap shuffling idea, but are just sort of another, let's say, flavor or version thereof. Okay, so the other thing that you can basically do is essentially rather than building sort of one very high-speed filter, build n filters running at the data rate over n. Okay, so this is basically sort of like a time interleaving type of idea, which hopefully you've heard about in the context of ADCs. Same idea here for FIR filters. So I'm just going to draw it for sort of a 2-tap filter, just because I don't want to do a big complicated drawing. But the idea is very, very similar, even if you do larger number of taps and larger ways of interleaving. Okay? So again, just to sort of give you the example, let's say that I take my input here. And so now what I'm going to do, and again, the advantage here is going to be that I'm not going to have cascades of sample and holds, but instead I'm just going to have one sample and hold at the very front. Okay? So let's say here that that's phi 0 and phi 1, and by phi 0 and phi 1, this will basically be just clock and clock bar here. Okay, but each one of these will be running at half of the data rate. Okay? So now what I'm basically going to do is, again, as I mentioned, instead of just building one filter, I'm actually going to build two filters, each running at essentially half of the throughput. Okay, so let's say that this was my A0 and A1. Okay? So basically what I would have here is, for this filter, which is kind of running conceptually off of the first clock phase, let's say that I want essentially the data and its first post cursor, right? Then what that basically implies is that because this is, again, and I'll just maybe draw the clocks here, phi 0 and phi 1. So phi 0 maybe looks like this. Phi 1 maybe looks like that. Okay? So basically, let's say that I was at this point right here, right? Then that would mean that my first post cursor, meaning, or rather I should say, the bit that came before me, was on phi 1, right? So in other words, if I wanted to build that filter, then I should just take this thing and feed it over here. Does that make sense to people? Or in other words, the sample that was on phi 1 is what happened one bit before me. So that's how I'm going to build my, let's say, something that has a z minus 1 in it, right? Okay, so similarly, you can imagine what you end up doing is kind of exactly the same thing on the other clock phase, just that kind of the meaning of everything is reversed, right? So in other words, here, my A0 would just be coming straight from that phi 1 sample, right? Because that's kind of my cursor, right? And my post cursor would be coming, would be coming from the other interleaved way, right? Because very similarly, if I was at this time, then one before me was phi 0. Okay? Does this sort of make sense to people? Or? Okay, so by the way, it's fairly typical, again, for this to be combined with a coefficient shuffling technique. In fact, you can imagine you can mix between any one of these multiple techniques. So you could have something that's interleaved and internally shuffled, or completely interleaved, or so on and so forth. But basically, all of these are just ways to try and deal with the fact that doing these long analog delay chains tends to be a fairly painful process from a noise and power standpoint. Okay? Does this make sense to everybody? Or? Yeah.
So why are these architectures being developed on the receiver end?
Okay. So there's multiple different reasons. So in the high-speed link context, it generally, as I mentioned, it generally is not used that often. But there's other contexts where it makes a lot more sense. So to give you an example, I can't always necessarily talk to my own transmitter, right? So if I need some sort of feed-forward equalization, which I'm going to need if I have any significant precursors in my channel, then if I want that feed-forward equalization, my only choice really is to build it on the receiver, right? Because if I can't tell my transmitter to do it, then I'm stuck. I just have to do it at the receiver, right? And by the way, I mean, you can see I complained a lot about it, but you know, for 2 taps, maybe even 3 taps, 4 taps, it's complicated, but it's not that bad, right? It's really only if you start talking about very, very complicated things, maybe 5, 10, 20 kinds of taps, that's where it starts really getting painful because the noise just starts to accumulate, right? So, as I said, it's not particularly popular in high-speed links simply because in links, many times, if not directly, maybe indirectly, you can actually go back to your transmitter and say, okay, you should be doing the following FIR filter to get to operate on this particular channel. Does that make sense? Or, by the way, there's actually some pretty clever things that you may even have to do to get the link to be able to talk to its own transmitter, because if you think about these big, complicated backplanes, your receiver may not, the transmitter associated with your receiver may not necessarily be talking to the receiver associated with your transmitter. So there's actually even things people did where they would have essentially a bidirectional system where in the forward direction it's your nice clean differential link, and in the reverse direction, whose only job it was to tell the transmitter what its equalization was supposed to be, was basically done on the common mode of that differential link. Okay, and so again, it's just a matter of being sort of clever to actually get the information you'd like to send back to the transmitter. Okay, but that can actually be trickier than you may first think it is. Does that make sense? Or?
Yeah.
Okay, great. Yeah.
So in the next one, do you have a mux at the output after that?
Not necessarily. So if you did something like this, what you'd typically do is your data receivers would basically be also de-interleaved. So let's say this would be phi 0, and let's say it would be phi 1, something like that. You could indeed reserialize it if you wanted to, but if you've already gone through the pain of generating all the clocks and stuff, you probably will end up doing something like this. We'll talk actually a little bit more about this.
Parallel ports kind of stuff, right?
Say that again?
It become like a parallel port kind of stuff.
Yeah, that's right. Basically, it becomes a time interleaved system,
Okay.
right? So this is valid at time 0, this is valid at time 1,
Okay.
and so on and so forth.
Okay.
As we'll actually talk about a little bit more later on, it actually does depend a bit upon what you're doing afterwards here. So if I'm really just making decisions, then probably it makes sense to do this, because kind of all of the latency and bandwidth of everything after the sampling point is relaxed, right? It's relaxed by about a factor of 2. Whereas if I reserialize it, then again I have to deal with the full bandwidth, right? But if, for example, I'm actually trying to build a DFE after here, not so clear that having the relaxed bandwidth helps, because as we'll talk about in 1 second, the DFE itself will introduce a bandwidth constraint. Okay? Yeah?
Actually, I got a question about this interleaving architecture. One of the problems was you have 2 paths right now, and then the elements not going to match each other. Do you actually care about that?
Okay, good question. So you were asking basically, well, hey, what happens if these elements don't really match each other? Can you deal with that? That's a great question. So it strongly depends on how you're basically setting these coefficients in the first place. So you can imagine if I have an adaptive algorithm that's going to be controlling these coefficients anyways, as long as I can control those 2 independently, and I can get error information from both of them independently, I may not really care that they're physically 2 different structures. But if my adaptation algorithm can't tell the difference, meaning it can only give me 1 piece of error information, then you'd really have to make sure that they match sufficiently precisely. So that's actually another thing that we'll talk a little bit more about, which is that depending upon how exactly this is done, it may be fairly easy to guarantee that matching, or it may actually be quite challenging. So as an example, okay, in the linear equalizers, that tends to be a little bit trickier because setting gains precisely is kind of tricky. But for example, if I had, in the DFE, if I had 2 sort of current steering DACs, I can probably, and those are really largely DC DACs, I can probably design them to match sufficiently well that I wouldn't necessarily have to adapt them individually. Maybe. Key difference being that's outside of the signal path versus this is all the high-speed stuff in the signal path. And so making it match that precisely is probably expensive from a power standpoint. It's a great question. Other questions on this? Or? Okay, great. So in that case, let's actually go ahead and move forward and actually really start talking about the DFE. And this is probably where we'll spend most of our time, just because this one, I shouldn't say it's really the most complicated, but it has the most, let's say, intricate design issues associated with it. Okay? So as I was kind of implying a second ago, if you look at a DFE, then the whole design tends to really be driven by the fact that you have to close a feedback loop. Okay? So just as a reminder, the way you would typically build these DFEs, and there's a few other ways as well, but this is kind of the most standard one, is you'll basically take whatever the input signal is, convert it to a current through just some standard differential pair, right? Then essentially, of course, you'll have a resistive loading. But then the way you'll build the FIR filter is much like we talked about building a FIR filter on the transmitter. Essentially, you'll take the digital data, and you'll just use that to steer current to one side or the other. So that essentially, if this current gets steered to one side, that's as if you're either adding or subtracting a certain value in the positive direction. Or if you steer it the other side, then it's obviously the reverse. Okay? So the whole trick here is that, again, basically this design is really driven by the fact that at every bit decision that you make, that new sort of stream of digital bits that's sitting inside of this shift register has to be able to create a new analog value that settles out before this comparator makes another bit decision, right? So in other words, if I'm going, let's say, 10 gigabits per second, then I basically have to make a decision, feed that bit back, update all the values in these sort of registers here, feed them through these current steering switches, and then get these analog values to settle to whatever the new analog voltage is supposed to be, all within that 100 picoseconds of time. Okay? So fairly challenging, particularly at very high bit rates, but nicely enough, this structure is actually very simple to analyze, basically for that exact reason. Because we know very well exactly what the sort of constraints on this structure are going to end up being. Okay? So in particular, if we sort of look at this analog piece right here, which is usually called the DFE summer, because this thing is just sort of conceptually, it's implementing this big plus function. Okay? So if we really focus on that piece, because that tends to be, at least from, let's say, making the design feasible, tends to be the most sort of critical piece. If we basically focus on that, then the key constraint is really related to what I just said. It basically says that essentially what I have to do is I have to make sure that this whole feedback loop here, whether it's from the comparator back through the first tap, or even actually from one of the flip-flops through here into the comparator, basically any one of those paths always has just one clock cycle to settle, right? So that means that the key constraint here is basically going to be that however much digital delay I have, for example, the clock to Q of the comparator, plus the analog settling time of this, node here, has to be equal to 1 t-bit. Okay? Does this make sense to everybody, or? Okay, so the other piece of, let's say, bad news here is, remember I said I have these analog voltages on the line here? I, generally speaking, want to settle those things out within this sort of analog settling time, meaning I want them to be fairly precisely the actual value that I said they were supposed to be, right? So that means that basically the amount of sort of, or rather I should say the time constant you have to achieve on this summing node isn't just sort of set by t-bit minus this digital feedback delay, but actually I need some number of those time constants within that t-bit minus the digital feedback delay, right? So in other words, if I look at the tau on that node, it has to be t-bit minus that digital feedback delay divided by some number which I'm just going to call n tau. Okay? And so just as a reminder, if you wanted to do, let's say, 98% settling, that n tau would have to be about 4. Okay? If you wanted, let's say, 90% settling, it would be like 2.3, right? Anywhere inside of that range, and you can kind of play around a little bit with that exact settling value. But typical number is indeed about 4 or so. Okay? So now, just to sort of make sure that everybody sort of gets why this is important here, let's say I was really talking about a 10 gigabit per second system. What does that mean the tau of this summation needs to be, approximately? What might be your digital feedback delay? Roughly speaking, let's say in a 65 nanometer technology. I heard somebody say it, just speak up.
8 pico?
Okay, yeah, probably about 20 to 30 picoseconds. So let's call it 30 picoseconds. Okay, so how much time does that leave for this DFE summer to settle at 10 gigabits per second?
70 pico?
Yeah, it leaves about 70 picoseconds for the DFE summer to settle. So if I want 4 tau of settling, what does my tau for the summer have to be? Roughly. It's not quite that bad, but it's close. Wow, I see. Really, brainwashed you guys or something. So I have 70 picoseconds, and I need 4 tau in 70 picoseconds. So what is that?
20, 17, 20.
Yeah, it's about 17 picoseconds, right? So what is that equivalently in bandwidth? Just call it 20 picoseconds to make your life easy.
Like 50 gig.
Okay, so it's 50 gigarad per second, which is 8-ish or maybe 9 gigahertz of bandwidth in sort of hertz, right? Because of the 2 pi factors,
Yeah.
right? So that basically says you need about 8 or 9 gigahertz on that one summing node here to actually make this thing feasible, okay? Now, by the way, I need not only do I have to get that sort of 8 or 9 gigahertz from just a standard amplifier, but remember, there's all these extra sort of current steering switches that I have sitting there, right? Each one of those things actually has some cap that it's going to be adding to your output. So that means that it's going to be even harder to actually get that speed constraint, okay? So actually, to sort of, turns out we can analyze that very nicely and come up with a pretty clean sort of, let's say, expression or prediction for what that's going to do to us, both from a power and achievable performance standpoint. But so before I dive into that, I just want to sort of briefly remind you guys one thing about, even if I just had a simple resistively loaded differential amplifier, kind of what sets the power consumption for that, okay? So let's just walk through that really quickly, because as you'll see, if you understand this, figuring out the sort of performance of the DFE and kind of what's achievable is also actually pretty easy. Okay? So let's just say I have something that, again, standard resistively loaded differential amplifier. And let's say that this thing is driving some explicit load capacitance. But let's not forget that any transistor that I put there will have its own self-loading capacitance. Okay? Okay, so first question, just if I ignored my own self-loading, or actually let me not even do that. So let's just say, let's assume that I knew what the total capacitance was. What sets the required GM?
Bandwidth.
Oh.
Bandwidth.
So when you say bandwidth, do you mean like just the bandwidth, or is the bandwidth times something?
Gain.
Yeah, it's the gain bandwidth, right? So just as a reminder, again, if you do GM over the total capacitance, then that's of course just the gain times the bandwidth, right? Okay, well, that total capacitance is of course just the self-capacitance plus the explicit load capacitance. Okay? Nothing magic there. Okay, so the only thing I'm going to do now is just, sometimes when people first look at this, they say, well, okay, this is kind of annoying because the self-loading capacitance is proportional to the size of your transistor, right? And so it seems like there's some iterative loop you have to do to solve this. Turns out you can just directly write the equation and solve it. Okay, so I'm just going to do a couple of steps to show you how to do that. Okay? So just as a reminder, right, if I say that I have GM over CGG, then you'll all happily tell me that, and CGG of course just means the gate capacitance, you'll all happily tell me that that's just the omega t of the transistor, right? Okay, well, so I claim I can always just model that self-capacitance as just being some factor, in this case I'm going to call it gamma, times the gate capacitance. Okay? So like, for 141 guys, that gamma is basically just CD over CG. Okay? Well, so if I do that, that then tells you that the self-loading capacitance is of course just going to be GM divided by omega t over gamma. Okay? And by the way, I just got there by saying that, GM over omega t is CGG. So if I want to get from CGG to C self, I basically just multiply it by that gamma. Okay? Okay, so this is now nice, because now I can actually write one expression that is just in terms of the GM. Okay, so in other words, if I just take that, and I just say that now, okay, GM divided by the total cap, which is just going to be GM over omega t divided by gamma, plus the real explicit capacitance, is equal to A times the bandwidth that you need. Okay? So from here, I'm just going to rearrange the terms a little bit. So I'm just going to group all the GMs together. And if you do that, then you just get something like 1 minus gamma times A omega bandwidth over omega t times GM is equal to A omega bandwidth times the actual explicit load cap. Okay? And by the way, again, all I really did there was just pull this up to the front and then subtract it off onto the other side. Okay? And then just regrouped it in terms of GM. Okay, so if you then use that, nicely enough, this gives you a very simple sort of answer in terms of how much power it's going to take you. Or rather, at least how much GM. So it tells you the GM is just A omega bandwidth times the load cap divided by 1 minus A omega bandwidth divided by omega t over gamma. Okay? So why did I spend sort of this much time deriving this thing? Well, this tells you actually some very nice, it gives you already some sort of nice intuition for how things behave in terms of how much power it takes you to get a certain bandwidth. Okay, or really a certain gain bandwidth. Because notice what this is really telling you is that this gain bandwidth here on the bottom is kind of getting normalized by the intrinsic gain bandwidth of the device, right? And in particular, notice that when A omega bandwidth is equal to omega t over gamma, meaning that this whole term here is 1, well, 1 minus 1 is 0, and 1 over 0 means it's infinite, right? Forget it, not going to happen. So this is basically telling you that no matter how much GM you spend, if you tried to get something that has higher bandwidth than that intrinsic bandwidth of the device, not going to happen, right? Not only that, it actually tells you, depending upon how close to that intrinsic bandwidth you're operating, it tells you exactly sort of how much extra power you have to spend due to the fact that the device doesn't have infinite bandwidth, right? So in other words, in particular, how close to the intrinsic bandwidth of the device do I have to be in order for me to spend sort of 2 times what I fundamentally would have had to spend anyways with a perfect device? By the way, maybe just as a reminder, how much power do you have to spend if you had a perfect device? And by perfect, I mean infinite omega t. What's power versus, or rather I should say, what's the GM you need to spend to drive a certain load cap with a certain gain bandwidth?
Great expression, right?
Yeah, which is what?
Gain bandwidth, I just,
Yeah, so just as a reminder, GM is always just gain bandwidth, or A times gain, well, I should say, I'll just call it gain bandwidth times load cap, right? And, for those of you guys who are, again, digital guys, I can turn that into CVF very quickly by just using a V star in one place, okay? So your GM is always just that A times, basically, the gain bandwidth times the load cap. So now all I'm saying is that, well, really it's not gain bandwidth times load cap. It's actually gain bandwidth times load cap times this 1 over 1 minus x looking kind of thing, where that x is your gain bandwidth normalized to the intrinsic bandwidth of the device, okay? So now, where do you have to be operating to make this penalty factor cause you to have to spend double the GM you otherwise would have had to spend?
1/2 omega t by
Yeah, exactly. You basically have to be operating at half of the intrinsic bandwidth of the device, right? So again, that's why I really like this kind of expression, because it really quickly tells you, without even knowing anything about what circuit you're building or anything like that, you just say, okay, look, if I need to be operating at half of the intrinsic bandwidth, ballpark, I can take all of my very simple calculations, multiply them by 2, and I'll actually be very close to the real answer, right? Okay, so just to make sure this is sort of clear, this is just saying sort of, on a slide exactly what I just said, which is, down when you're at these sort of relatively low gain bandwidths, everything just scales with how much load cap you're driving. But as you get closer and closer to sort of the intrinsic limit of the technology, things just start to explode, right? In other words, at these points, no matter how much power you end up spending, you just can't possibly get that intrinsic, that much gain bandwidth, because basically the self-loading of the device is what's limiting you, okay? So now is where we come back to the DFE, right? So with the DFE, we don't just have this sort of simple amplifier, right? What we actually have is an amplifier driving a bunch of these other switches, right? So all of those parasitic capacitance from the switches are basically going to slow down what's the sort of intrinsic bandwidth you can actually really achieve on that DFE summing node, okay? So what I want to do now is actually just really quickly, turns out that we can use this to also actually very quickly derive basically what is it that actually is also achievable for you to do in the DFE, and how much power will that actually take, okay? So let's just sort of quickly walk through that. So I'm just going to draw everything single-ended because, I'm lazy, but you can imagine it's kind of exactly the same thing with a differential version. So basically, my summer, at least from the standpoint of the analog input, really just does look like a differential amplifier, okay? But then what I'm basically going to be doing is I'm actually going to have a bunch of these current steering switches that are basically going to either have some current flowing through the thing, depending upon the value of that data, or not, right? So as an example, this will be some like previous tap data that controls that switch. And then there's going to be some amount of current, which I'm just going to call I tap here, which is going to be flowing through that output to basically create the analog either summation or subtraction, okay? Does that make sense to everybody, or? Okay, so the first question is, how do I pick the value of that I tap? Like, what's going to be setting that value? How do I decide that?
Your channel coefficient.
Yeah, exactly. So that I tap is just going to be set by whatever the coefficient you're trying to create is in the first place. Okay? So now, if I told you how much, let's say, it's actually not really bias current, but what you're basically saying is that, look, this I tap is just going to get multiplied by RL to create some voltage, right? But the coefficient is usually normalized to sort of what my input amplitude was in the first place, right? So the way this actually turns out to work is basically what you really have to keep track of is, and let's call this V out over here. What you really want to know is, what is the output voltage basically due to the cursor, right? Due to the input signal that's only due to the cursor, okay? Well, assuming everything remains reasonably linear, then of course that's just GM times RL times whatever the voltage of the cursor is, right? And when I say the cursor, I really mean just the cursor. Because remember, this input is still corrupted by ISI, right? So you can't just look at the peak-to-peak swing there. You actually have to look at what just the value of the cursor actually is, okay? So that's the output voltage due to the cursor. And if I want to subtract a certain amount of ISI from that, then basically what we're saying is that there's some output voltage we want to create due to the tap, which is just going to be equal, of course, to I tap times RL. Okay? So, in other words, let me just sort of assume that the amounts of voltage you want to cancel, meaning due to the DFE, meaning, or rather I should say due to the ISI, normalized to the cursor, let me just define that as being some M DFE. Okay, so for example, if you had a channel that looked like, let's say, like this, where this was 1 and this is 0.5, that M DFE would be 0.5. Okay? If this value was, let's say, 0.25, it would be 0.25, and so on and so forth. Okay? So by the way, again, I'm actually drawing this all just for one tap here. But what you're going to see is that the way I'm going to deal with multiple taps is just by keeping track of how that changes the total MDFE that you're dealing with. In other words, if I had, let's say, several more taps, I would just sum all of their relative values up compared to the cursor. And then basically the size of the switches that I'd have to use would all be sort of proportional to that relative amount of signal that you're canceling. Does that make sense to people? Or in other words, if the sum of all of the values of the, or I should say the absolute values of the ISI afterwards, if that was, let's say, 5, then I would use an MDFE of 5. Okay, meaning 5 relative to the cursor. Okay? Okay,
Just
so,
a question.
yeah, sure.
So we're trying to calculate what that approximate loading cap will be? Is that
So what we're going to do now is just like 2 slides ago we calculated what the GM needs to be as a function of where you're operating relative to the gain bandwidth. What I'm going to do now is, as a function of this MDFE, I'm also going to calculate what the GM actually has to be. And in fact, I'll recast it so that it'll be more directly in terms of what's the bit rate you're operating at, what the digital delay is, and things like that. And you'll see it'll be a slightly complicated, but it'll be like a one-line expression. Okay? Okay, so basically if we just use this, then we can say that that tap current is just going to be MDFE times the GM times essentially the cursor voltage. And notice, of course, the load resistance drops out because it just scales both the cursor current and the DFE correction current by the same amount in terms of voltage, right? Okay, so now I'm going to do something that's a little bit funny. I'm going to, even though I'm not really generally operating that switch necessarily in saturation, although you could, I'm just going to figure out sort of what's the GM I need from that switch. Because once I do that, I can then sort of figure out what's the parasitic capacitance from that switch, again, based on the omega t. Okay? So if I know what the tap current is, then I can kind of say that the GM of that tap device is just 2 times, of course, that current, which is MDFE times GM times V cursor, divided by the V star of that switch device. Okay? And again, I'm only doing this because I wanted to just recast this into a form where, notice, now that I've gotten it proportional to GM, then I can basically figure out how big is the load cap from this switch relative to the cap from the input device itself. Okay? So in other words, I'm going to have some C self from the cursor here, and I'm also going to have some C self from the tap. Okay? So just like before, the C self from the cursor, that's just going to be GM times gamma over omega t. right? And then for the tap, it's going to be something, of course, very similar, which is just whatever the GM of the tap is, divided by the omega t of that tap device, times, of course, gamma. And I've just done things a little bit differently here because you might be using a different V star for that switch device than you are for the input device. So obviously the omega t might also be different. Okay? And so now, just as a reminder, if I just plug things back in, that will just be m dfe times v cursor divided by the V star of the tap times gm over omega t of the tap times gamma. Okay? Everyone tracking so far? Or? Okay, so now, as you can see, I've gotten both of the self-loading terms to be proportional to gm. So just like I did before, I can just rearrange everything and do the subtractions and all that. And if you do that, just the details there are actually not that difficult. If you do that, what you'll end up with is something like the following. So the GM that you need, as before, on the numerator, that's just sort of, you need some gain, you have some load capacitance, those are just going to be proportional. The only thing I'm going to do is that now I'm going to remind you that, and I'll do it up here, the bandwidth you need from the summer node is again going to be n tau divided by the bit time minus the digital delay. Okay? So I'm just going to write everything in terms of that so that we can see sort of directly how those things come into the picture. Okay, so that will just pop up on the top, and that's really just for me plugging in what the bandwidth was supposed to be. Okay? And now on the bottom, just like before, I'm going to have something that looks sort of like 1 minus x. It's just that the x is going to be more complicated. Yeah, question?
Like 1 over that or something?
Okay, it's very close. It's just that because I have this extra term over here, before I used to have just something like a, n tau over t bit minus t digital divided by essentially omega t over gamma, right? That's kind of what I would have had just from the straight differential amplifier with that bandwidth. Well, now it's just you have to multiply that by 1 plus essentially something that's just set by the ratio of this capacitance to that capacitance, right? Because now I have this extra self-loading due to those taps, okay? So if we just write that out, that just ends up being 2 times m dfe times essentially v cursor over the v star of the tap times essentially the omega t of the input device divided by the omega t of the tap. Okay? Does that make sense? Or?
Sort of. I'm still not getting where the... Why do you have tau in there still?
Okay, so
oh, you're saying in... sorry. It's a subscript.
That's right. It's the number of tau. That's right. It's just that number, which is 4 or 3 or whatever it is. Stephen? Yeah.
Wasn't the point to substitute the CL with the C self in the numerator?
Well, so notice the CL only appears up on the top over here.
Okay.
Right? Because the CL basically is just saying, if I have double the explicit load cap, that never causes a bandwidth limit. It just means that I have to spend twice as much power as I did before to get the same bandwidth. Right? What causes the bandwidth limit is if I upsize my device and I increase my own self-capacitance by that same, let's say, factor of 2, if I'm dominated by driving this, then now I'm screwed, right? Because I can't independently change my GM from my load cap. Does that make sense? Or? And so notice the same thing sort of happens with the DFE because the amount of current you have to use in that DFE is also proportional to the GM you had on the input device in the first place, right? In other words, what the DFE is really doing to you is it looks a lot like just a differential amplifier or a standard common source amplifier, except that now the actual sort of intrinsic bandwidth you can get is degraded by the amount of correction that you have to do, right? In other words, you can imagine that if I have to correct something that's like 5 times the cursor, 10 times the cursor, 100 times the cursor, that's just directly degrading the sort of intrinsic bandwidth that you can actually achieve out of that device. Does that make sense to people, or? Yeah.
So if you have more than one tap, so wow, which digital delay will you use?
Say that again?
If you have more than one tap, which digital delay will you use? I mean, there are like-
Okay, so that's a great question, and actually we'll talk a little about that in a little bit more in detail. So, and we'll go back to the picture we had over here. So what your question is really getting at is, well, look, there's kind of there's different digital delays, right? There's one digital delay for that very first tap, and then everything else is kind of a little bit different because that's just straight off of a digital flip-flop. Okay, so you can imagine that if I really did something like this, well, which one are you going to have to use?
shortest one.
In terms of the digital, shortest in terms of the settling time, or shortest in terms of the digital delay?
Digital delay.
No, it's actually the shortest settling time. Right, because
I mean,
let's
the
say that this
shortest
thing
loop,
is
right?
longer,
Okay.
and I want that to settle, then I have to
sorry,
settle
yeah,
within
right,
whatever time is
right,
left. Right? So we'll actually talk about exactly that issue in 1 second, because it turns out you can imagine that is usually longer than the clock to Q delay of the flop. Right? Because for all intents and purposes, this is a flip-flop just with a really small input voltage. Right? Okay, so again, what I actually really like about this particular formulation is that it again tells you very quickly, okay, how much power does it take you to build a certain type of DFE with a certain amount of correction that you're going to be doing? And in fact, again, it's really easy. Once you know what the load cap and the sort of gain bandwidth you need is, you can then figure out, okay, well, how much power would that take just based on this sort of relative factor on the bottom here. Okay? The other thing that's actually kind of nice about this is that it also tells you that because this term sort of appears down on the bottom here, and again, it's sort of degrading your intrinsic bandwidth, it tells you that if you try and cancel too much residual ISI, at some point, no matter how much power you spend, you just won't be able to do it, right? Because you'll just be completely self-loading limited, okay? So this is actually just sort of a plot using some, let's say, reasonable technology numbers of just saying, what is the maximum sort of relative magnitude that you can actually correct for, given a certain amount of, let's say, digital delay and given a certain technology and things like that, okay? So what you can kind of see here is that, you know, as long as my MDFE is relatively low, then the amount of extra power I have to spend in my summer, which I've just represented here by sort of how much GM, you know, it's increasing linearly, but it's not too big of a deal, right? And then at some point as I start getting really close to that intrinsic bandwidth limit, well, guess what? No matter how much power you spend, you just can't possibly correct that much ISI, okay? And the only thing that I've changed between these curves here is that basically I'm changing the amount of digital delay that I'm handling. Okay, so in other words, if I have a really fast digital delay, then I have more time to settle, and that means that I can handle larger residual ISI. Okay? So there's one other thing that we have to sort of be a little bit careful about here, which we sort of talked about in the context of the transmitter, which is right now I've just quantified everything as just sort of this maximum correction that you're doing, right? Unfortunately, life is actually even worse than that. Because, indeed, if I told you that you were operating over, let's say, the following channel, where this was, let's say, 1, and this was, let's say, 0.5, and let's say this was 0.25, right? If I gave you exactly that channel, then you would go, you'd build your DFE, and you'd make it so that you would cancel exactly only 0.75 of relative ISI, right? So there, great. If you can do it, great. If not, then there's nothing else you can do anyways, right? Well, but remember, you're probably not going to be building this link to operate on just one channel, right? In reality, there's going to be another channel that, let's say, may look like, I don't know, oops, may have the following characteristic. It may instead do something like, okay, maybe that's 0.6 and this one is 0.1, right? And let's maybe even add another tap over here of, let's say, I don't know, 0.2. Okay? Well, now notice life is actually much worse than you might have thought. Because for each one of these taps now, you actually have to handle the worst case on any possible channel. Right? In other words, for each one of those taps, whatever any one of the channels could be, you better make sure you can handle that. Right? So now if I give you a big whole range of channels, then when you actually calculate this AMDFE, you can't just look at it on any one channel. You actually have to look at it over all of the possible channels you might be dealing with, right? So then you can imagine, even if each individual channel is not that bad, if you concatenate all of the worst cases for all of the channels, pretty quickly this number can add up and be something that may be too large for you to actually deal with. Okay? The good news is that actually, even at this 10 gigabits per second, which is pretty actually fast for this technology, you still actually can cancel a pretty large amount of relative ISI. So even with about, let's say, 50 picoseconds of digital delay, you can still get up to about 6, basically an MDFE or a relative ISI of 6 times the cursor, which again is pretty large, but once you include all these worst case effects, maybe about where you land in any case. Okay? Does that make sense to people, or? Yeah.
What do people generally assume about these links when they are designing them? I mean,
Okay. Well, so it depends obviously who you talk to, but if you're an industry guy and you want to sell as many parts as you can, you want to find as many channels as you can that you're actually going to operate correctly over, right? So you'll go and you'll try and find, well, what is the, let's say, the 36-inch backplane with multiple stubs, and what is the 8-inch, short channel, and what is the, let's say, cable thing, and so on and so forth, right? The good news is, again, you usually know reasonably well sort of what those channels tend to look like. But nonetheless, that does mean that there is a pretty wide range of worst cases that you might actually be handling, right? So that would basically mean that you should take this kind of analysis and figure out, okay, well, what is really the maximum amount that I can actually reasonably cancel? And by the way, sometimes what will actually happen is that even if these all end up being small, there's kind of a minimum size device you can put on any one node. And there's kind of a minimum length wire you need to just route that thing across that, whatever device pitch it is. So even if it's not, because of the fact that there's really that much ISI there, just because of the fact that there's a minimum size device, every time you add a tap, that may have a certain minimum relative strength that you're adding. Okay? So kind of the key insight here is that this tends to mean that, let's say from a practical standpoint, this tends to really mean that there's kind of a maximum number of taps that you can do in any given technology at a given data rate. Okay? That's practically sort of how you will tend to use this the most. Okay? Okay, so
Sorry,
if
one
oh
more
yeah,
question.
sure.
Back on the previous slide.
This one or even one more back.
One more back.
Okay.
So that switch is really like a digital switch, though, right? So you always get its capacitance, but you may also get the capacitance of that current source.
Okay, that's a great question. So it turns out that basically for exactly the reason that you're asking about, and actually some things that we'll talk about a little bit more on, it turns out that even though I've said that this thing is hard switched, you tend to actually want to keep it in SAT. Okay? Because indeed, you're right, you'll pick up all of the parasitic cap from that tail current source right there. And by the way, this might be, for reasons that we'll talk in more detail a little bit later on, this is really obviously a digitally controlled thing. And let's say it's about a 6 or 7-bit DAC. There might actually be a lot of parasitic cap on that node. And in fact, you may even want to pull this thing so that physically in the layout, it's sitting somewhere halfway across the chip, just so it's not screwing up your nice, clean, high-speed signal path, where you want as small of a parasitic cap as you can get. So you're absolutely right. If you really hard switched it, then you might actually be asking for trouble. So indeed, you typically will tend to leave that in SAT just to act as sort of a shield from all of the junk underneath it.
So you sort of keep it higher impedance than the load?
Exactly. Exactly.
So depending on the data pattern, your output impedance on a total...
Okay. Great question. So, and actually this will be, let's say, I'll have to go back to this other picture to really make that more clear. You're saying that, look, each one of these switches could be flipped one way or flipped the other way. And so I could have one data pattern where, let's say I had 20 taps, where 19 of them are flipped one way, and I'm just flipping one of them back and forth, right? Yeah. That will be very different than having 19 of them flipped the other way and flipping one back and forth. You're absolutely right. That will indeed be basically what will modulate that impedance on that node, and it'll cause nonlinearity. But there's one very beautiful thing about this particular structure. What am I going to do immediately following subtracting that current out? What's the next block I go into? Yeah, I'm making a bit decision, right? Exactly. So do I care if it's nonlinear at that point? I'll be a little bit careful. I only care in the sense of it'll change my amplitude, right? So it'll make my amplitude a little bit smaller, but as long as my voltage margin with that degraded amplitude is good, I don't care. Okay, so that's actually a very important point which is one of the, let's say, subtleties, but really beauties of this structure, is that in terms of the current, I'm really adding all the currents linearly. So the subtraction I want to do in terms of the signal processing is correct. The only thing is that afterwards, I'm going to distort it through some nonlinear impedance at that node.
Which means your voltage amplitude could be smaller, right? For those signals with relatively small voltage margins, then you couldn't make an error, right?
So you are right that if the nonlinear impedance of that node is sufficiently low compared to your load resistance that you basically don't get the amplitude you want, then that indeed would be a problem.
Okay.
But that's a much easier problem than actually making this a truly linear summation.
No, it's not necessary to make it linear.
Exactly.
Just,
No, that's absolutely right. Yeah.
Actually, just follow on that. Once you actually modulate the on impedance, doesn't you kind of change the coefficient you want it to be because it becomes less efficient?
So that's the beauty, is it doesn't actually change the coefficient because if I drew sort of the equivalent model of this, right, all of these are basically steering currents, right? So I can take all of those currents and dump them all into some node, but all that nonlinearity is doing is modulating that resistance, right? So in other words, what I'm basically saying is that the addition itself, because that's all happening in the current domain, that addition itself is linear. The only thing that's nonlinear is converting it to voltage afterwards, which means that the coefficients are also actually correct. So again, that's a great question because that's one of the subtleties of this particular structure, which is something you have to be careful about because, as an example, if you don't sum everything in the same place, you actually do it in physically different places with different impedance variations, now bets are off. Right? Now the nonlinearity actually will come into the picture.
Question.
Yeah.
If you keep the switches in the saturation, why do you have nonlinearity?
Because their RO is not infinite.
Which RO you're talking about?
Just the RO of
RO
the
the-
current steering switch of this device. Right? Or to be that other picture of these devices. Right?
Or you're just saying the nonlinearity from the GM and RO of the transistor?
Not from the GM, just from the fact that, as an example, remember, there's some data pattern that's in the shift register here, right?
Yeah.
So let's say I had 20 taps. It could be
Yeah.
that I have 19 ones and 1 0. And then that 1 0 I flip from being a 0 to a 1, right? The voltage impact of that would be very different than having 19 zeros and flipping the last tap from a 0 to a 1.
Okay.
Right? That's the nonlinearity I'm referring to.
And I have so that nonlinearity is worse than GM of your preamplifier.
It depends. It's not really, let's say, necessarily worse because it really strongly depends on what the RO of those switches are
Okay.
and what's the V star of those compared to the V star of the input device. You know, exactly how big that nonlinearity is really strongly depends on the exact design you're doing.
Okay.
In practice, you can actually do a very large number of taps and not necessarily have it be too big of a problem, except as long as it doesn't cause you to compress too heavily.
Another quick question. So.
Yep.
What do you said that the settling of the last tap there has to be 4 times smaller than the bit than the T bit there. But what do you usually set the bandwidth of the preamplifier?
Oh, you mean inside of the comparator?
The one in front of the comparator.
This here?
Yeah.
Well, this bandwidth is just set by this resistance, right? So basically, the bandwidth on this node is exactly this number that I'm quoting here.
So.
You are right, by the way, that there may indeed be actually another preamp inside of the comparator, which would then mean that that also has an implication on how fast this can settle. But the good news is that's also fairly straightforward to figure out what the impact is. You can kind of include that as a digital delay if you like.
Okay.
Does that make sense? Or? Okay. So maybe I'll just ask you guys since I don't think you actually have the slide. So we said that one of the big problems here is that, again, I have to deal with sort of this worst case condition over all possible channels. And we said that particularly in the DFE, because I have to close this loop so quickly, having all that extra parasitic cap is actually kind of a bad problem. So what's actually a technique that we already learned about that you could potentially use to try and make things better from the standpoint of the DFE? And in particular from the standpoint of reducing the parasitic cap on that node. Yeah?
Carry look ahead adder kind of thing.
Okay, that's a different issue actually. So that one we'll come back to in 1 second. You said carry look ahead adder. That's actually loop unrolling. We'll talk about that in one more second. But I'm actually still talking about just, you know, let's say that I try and build this thing, and I look at my channel and I figure out, or rather I look at all of my channels, and I figure out that over all of my channels, just the worst case on each one of them, when I add those all together, is just too large. It's just too much capacitance for me to actually close the loop at that speed. What can I do?
Like the shuffling stuff?
Similar.
Cascode?
Okay, that actually also turns out to work, but for a different reason. What do you remember we talked about the transmitter? And there was kind of this continuum of things you could do in the transmitter.
Kind of multiplex the digital inputs to multiple.
There we go. Exactly. So right, you remember with the transmitter we talked about how if I just had like a DSP and a DAC, that DAC would have like the minimum parasitic capacitance you could possibly get, right? Because you'd know exactly what the range that DAC actually needs to handle is. Well, so same thing here. What you can basically do is take all the techniques we talked about in the transmitter. So for example, multiplex different digital inputs into these actual analog taps, just to reduce the amount of extra cap you place onto that summing node, right? Because in this particular example, I made it so that, even though I have a pretty wide range of coefficients I can cover, I'm only paying something like, 1.25x of kind of this peak value in terms of parasitic capacitance, right? So, just as a reminder, this picture that I'm drawing here was exactly the picture I drew at the transmitter. I've just folded it to now be in the DFE feedback at the receive side, okay? So all the tricks that we talked about for sort of how you build FIR filters and minimize parasitic cap at the output node, all of that stuff directly applies to the DFE as well, okay? The only thing which you should keep in mind, which I reminded you all on the transmit side as well, is that any of these tricks that you play is always a trade-off between how much parasitic cap is on this node and how much power do you spend in this digital stuff in front of it to support all of these different configurations or logic that you're doing on it, right? And again, in the limit, it would just be you'd have a big digital signal processor here that would generate some number of bits, and then you'd feed it into a DAC, right? That would be like the minimum parasitic capacitance you can get, but the maximum amount of digital power that you could be spending. Yeah?
So that also adds digital delay, right?
That's right. This also shows up as delay in your feedback path. Now, turns out there's again some tricks you can play here, because, for example, notice that on this first tap here, which tends to be the most critical, I didn't put any muxing. Right, well, okay, actually, to be fair, I actually did because I put a D0 there, so I didn't play that particular trick, but you can imagine there's some games you could play where you do the muxing at earlier points in the feedback chain and then move flip-flops around. There's lots of games you can play there, but you're absolutely right. Anything you do will also have implications on what the digital feedback delay may end up being, which is absolutely true. So, by the way, for most of the technologies I've seen, it turns out that you can actually do some pretty complicated DFEs, so that most of the time actually doing this stuff in the digital probably isn't worthwhile. But if you push on the speed enough, so that it's just not feasible to build this thing anymore, those type of techniques may become just a necessity just to make it even possible for you to actually get the DFE to work at this speed. Yeah?
So why not just use the inductor there?
Oh, on this node?
Yeah.
Oh, absolutely. Put an inductor there. You'll get 1.5x of what you could do before. And then eventually you'll again run into the same limit. So that's absolutely, don't get me wrong, you can do all the peaking, you can do all the high bandwidth tricks that you'd like to do. I will mention, however, that inductor will probably be, 5 to 10x larger than the rest of the circuit. But yes, you can absolutely play those tricks. I'm not opposed to it. I'm only, unless you're really pushing on the speed, that tends to be just expensive from an area standpoint. Other questions on this, or? Actually, I was a little bit mean. All the stuff you can do to do high-speed amplifiers applies to this too, right? Because anything that you can do that gets you closer to that intrinsic bandwidth is just as beneficial here. Okay? Okay, so now's where we sort of get into what maybe Charles was hinting at a little bit, which is, and actually I guess a few of you have asked already about, which is, so far I've just been talking about sort of, what does that summer sort of look like? What's kind of the constraints on it? Turns out there's one thing which is almost always the really nasty thing to deal with, and that's always closing that very first tap. Okay, and so to kind of highlight why that is, let's just kind of draw a little sort of block diagram of what this thing looks like. So the DFE, I usually go into some summing amplifier. Right, then again in the current domain, I'm going to subtract off whatever that ISI is. I will still tend to go through a preamp before I go into the comparator. There's some more detailed reasons why you'll do that, but for now, just take it as because I don't want to have to deal with a kickback. Okay, so I'll go into a preamp, and then essentially I go into the actual slicer, and then at that point I have to feed back and go through. I'll just label this as being an FIR. It's not really necessarily in the digital domain, but you get the idea. Okay. So for that very first tap, things tend to be a bit nasty for kind of the following reason. Okay? So we've already said that this DFE summer here is sort of self-loaded because of the taps. Right, so in other words, there's kind of this intrinsic speed limit, or really, if I get close to that speed limit, it starts costing me a lot of power to actually do it, right? Okay, so now, if I look inside of the preamp, if I really sort of do this, let's say, the way that we talked a lot about in 240, first of all, I try and make that thing have a pretty high bandwidth, but, which means that I have to spend some power because I'm worried about kickback, right? So I want a low impedance there. But at the same time, this is also a convenient place for me to do offset cancellation. Well, that means that that preamp is going to be loaded by those offset canceling devices. Okay? So again, it's also going to be sort of, it's going to actually tend to be quite fast, but still has some loading that it has to deal with in terms of power and speed and etc. Okay? Well, so now if we look inside of that comparator, remember, I don't want to be dealing with huge swings. Because if I do, then that implies that my transmitter has to be sending huge swings, and I'm just going to be spending lots and lots of power. Okay? So if I look at that comparator, there's going to be some minimum amount of time it takes me to just resolve the small input signal. Right? And that minimum amount of time is going to be something like, let's say it's, some, whatever my input swing is, let's say divided by 2. That's, of course, after the DFE. Oh, sorry, excuse me. So in other words, if I have some peak swing at the output, then whatever that peak swing is, I have to at least get, okay, nominally eventually I have to get it to full rail, but maybe from a digital delay standpoint I only have to go half of the way, right? But the amount of time it's going to take me to do that regeneration is going to be at least this, right? In other words, it's going to be just some minimum amount of time it takes you just to get that small signal back up to the large enough rails. And by the way, you're not even actually done, because now, even in this FIR filter for that very first tap, I've got these digital swings that I'm trying to feed back into those switches that I'm generally trying to keep in SAT. So I might actually need to put some either buffers or level shifters or something like that, just to make sure that my analog, summing nodes are still behaving the way I want them to. Okay? So that's not to say that, this whole thing is impossible to actually close. You can indeed do it. But it tends to be pretty tight. Okay, and in particular, having to regenerate that small input signal can cost you quite a bit of time in terms of just regenerating, let's say, from 10 millivolts or 5 millivolts all the way up to something like a volt. Okay? So the issue you really run into here is that if you're running that DFE, you can kind of notice, if you're running that DFE kind of close to the self-loading limit, but now you say, oh, no, oops, sorry, actually my comparator is a little bit slower. Right? In this case, just, let's say, 10 picoseconds slower. All of a sudden, you might actually be completely infeasible. Right? So especially if you have to deal with a lot of taps at that summing node, closing this whole loop can turn out to be quite challenging. Okay? So from that standpoint, there's a whole series of techniques that people have come up with just to try and basically deal with that very first tap. Okay? Because, again, that very first tap just tends to be kind of the trickiest one to really deal with. So the first one, which is at least relatively straightforward to do, is what's called a split summation architecture. Okay? So the idea here is pretty simple. So what you basically say is, well, okay, I'm still going to do most of the work of the DFE in that summer. And you'll see why I labeled this as sort of, a slightly funny way in 1 second. But just for the very first tap, because in the preamp I know that I maybe am only dealing with that one tap and maybe with offset, it's going to be easier for me to get a very, very high speed time constant, okay, a very small time constant. So what I may basically do is, and let's just say that my first tap value, let me just call it, let's say, A0, okay? What you basically do here is you just split it so that most of the work of the DFE, meaning most of the cancellation, is done in this first summation path. But just for that very first tap, you cancel it directly inside of this preamp loop here. Okay? And again, the reason this is potentially advantageous, and I should mention this was sort of first done by a guy named Brian Leibowitz. This was presented at IC about 4 years ago. the reason why this is potentially advantageous is just since I know I'm only dealing with this one tap here, it's much easier for me to get very, very high throughput onto that preamp. Okay? Does this kind of make sense to people, or? Yeah.
Does this kind of like go against what you just said, like something like the current in the same place?
So absolutely, this does the only, or let's say it depends on how big the ISI is, but the only issue with doing something like this is that now, unfortunately, you're going to go through some nonlinearity getting from here to here, and you will still have that ISI left. Right? So if that nonlinearity is big enough, then that could indeed cause this to not actually work. In most link channels and kind of most of the swings that I deal with, that's not too bad of a problem. But you're absolutely right. If I have a really nasty channel that would have huge nonlinearities right here, then indeed that might not actually work. So that's absolutely correct. So this does indeed suffer the issue of now you're summing at two different nodes. You have to be really, really careful about the nonlinearities. It's a great question. Other questions on this, or?
So what is that label?
Say that again?
The labeling.
The label, I just said it's 2 through n, meaning that it's taps 2 through n rather than the very first tap. All right, so in other words, there's at least one delay in this FIR filter here before you correct all of the residual ISI. Okay? So indeed, there is that issue of, well, okay, what happens when, things are slightly nonlinear, so you can't really do that, or potentially that will cause an issue here. Or in fact, just if you start pushing this to a high enough speed, then particularly if you try and use something like a strong arm latch inside of that comparator there, it can just start to get pretty tough to actually hit the speed that you need. Okay, and largely that's because, if you want to take a 10 millivolt input and regenerate it up to a full 1 volt of swing, that's a reasonable number of tau that you have to work with. It's about 4 or 5 tau that you need to resettle. Okay? So because of that, there's actually some people that were even more aggressive, and particularly for that very first tap, they did what I sort of term as being an all CML design. Okay, so this particular design ended up being a lot of power. I don't think that necessarily is fundamentally the case, but basically the idea here was that if you use a CML latch instead of a strong arm comparator, turns out you can actually make that thing faster simply because of the fact that your swing is lower at the output. Okay? So if I have to regenerate to 200 millivolts instead of to a volt, that's a couple of tau I buy back, right? And if I'm really pushing on the speed, then actually that might be a reasonable thing to do. Okay, so this thing looks a little bit funny. It turns out it's actually not that complicated. All it's really doing is something like the following. Okay, so you basically have this input sort of summer amplifier that then essentially goes into the first CML latch or flip-flop. It then comes out through, and actually I'll call this a flip-flop because that's really what it is. It then comes out through a buffer. And then that buffer just feeds, and actually I'll draw it a little bit over here. That buffer then just feeds back to essentially what you can think of as being the current steering switches to subtract off of that analog summing node right there. Okay? There's some additional tricks they played with like bias currents and things like that. Don't worry too much about it. Really the key point here is that if you're really pushing on the edge of the speed limit of the technology, then simply replacing the comparator itself with something that has lower swing at the output, just to reduce the number of tau of resettling, could actually be a beneficial thing to do. Okay? And in this particular case, just from a sort of practical standpoint, the common modes also tend to work out relatively nicely, because now I have a CML stage driving another sort of CML stage in terms of the current switching. These are the current switches right here. So from a common mode standpoint, I don't have to worry too much about pulling those things out of SAT and things like that. Okay? So again, this particular design, you can maybe have some questions about, sort of how much equalization it was really doing and things like that. But it was showing that actually something like up to about 20 gigabits per second was actually possible even in a 65 nanometer CMOS technology. Okay? So just, to put that in perspective, that's 50 picoseconds for everything, right? Decide, feedback, resettle, all within that 50 picoseconds time. Okay?
What's the power?
I don't remember. It wasn't too bad. It was maybe, I think the whole thing was maybe 30 or 40 milliwatts. Does anybody happen to remember? Oh, no, but that was with the transmitter and stuff like that, right? Okay, I don't remember precisely. I think the equalizer itself, like just this piece by itself, and actually maybe we can even figure it out because they gave us nicely enough in one place the bias currents. But I think this whole thing was maybe on the order of 20-ish milliwatts or so, somewhere in that ballpark. And by the way, you can work out exactly what the numbers should be just based on the kind of the design equations we went through. But it's in that ballpark. Okay? So indeed, you can actually get up to some pretty high speeds, but even that sometimes is just not good enough. Okay? So we'll basically close with this for today, but the last technique you can actually pull, which again is really mostly focusing on that very first tap, where it's just hard to actually get that kind of speed, is what's called loop unrolling. Okay? So this idea is actually very, very similar to what you do in carry look-ahead adders. So the idea here is the following. You basically say, well, if I'm dealing with just 2 PAM signals, meaning just 2-level signals, then there's really only 2 possibilities. Either the previous bit was a 1, or it was a 0, right? So why don't I just compute the answer for both possibilities, and then just after the fact, pick the one that was actually the right answer. Okay? So the way this works out is something like the following. What you basically do is you say, okay, well, I'm just going to build now, instead of having 1 comparator, I'm going to have 2 comparators. What I'm going to do is shift the thresholds of those comparators by basically the value of that ISI that I'm trying to cancel. So in this particular case, and you may hear this more often, this is for what's called a 1 plus alpha channel. So alpha is just the coefficient of that first post cursor. Okay? So if that's the value of the coefficient, then the way you'd build this is you'd say, well, let me just take 2 comparators. One comparator, its threshold, I'll shift by plus alpha, which means that I'm assuming that the previous bit was a 1. The other comparator, I'll shift it by minus alpha. Oh, excuse me, I'm sorry. Plus alpha meaning I assume the previous bit, oh no, that's right, was indeed a 1. And minus alpha, I'm assuming the previous bit was a 0 or equivalently a minus 1, right? So in other words, I'm just sort of, by shifting the threshold, I'm kind of creating that subtraction. But then after the fact, once I know what the correct previous bit actually was, I go back and select what the new current correct decision actually is. Okay, so again, just like with a normal DFE, this is completely recursive, right? Because notice I need to know what the previous bit was to select the current correct bit. But that's no different than what we were doing in the analog domain as well. Okay? So the trick here is that now I've kind of removed the analog settling time from the picture because I'm just statically selecting between these 2 coefficients that I'm just statically going to set. Okay? So now I've just sort of pushed the timing path to be purely this digital loop that may actually be much easier for me to get closed. Okay? Does this kind of make sense to people, or? Yeah.
How do you treat all the other tabs?
Okay. So that's a great question. We'll actually draw that next time. But what you'll typically do is you do this, for example, on the very first tap, and then all of the other ones you'd actually do in an analog summation before it. Okay? Turns out you can actually do more than just 1 tap, loop unrolled. You could do 2 taps, you could do 3 taps, you can do 4 taps. But as we'll draw next time, the number of comparators you need scales as 2 to the n taps that you've unrolled. Right? So that's why you tend not to do it for too many of them. That's a great question. Okay, so we'll pick back up on Thursday, so I'll see you guys all then.